This video is going to go through the 3-3 warm-up and then the notes for 3-4. Make sure you're completing both of them so that you can submit those for the assignment for today. So number 1 and 2 say rewrite and simplify. So there's a lot of different ways to do this, but we're going to rewrite them by practicing the expansion or condensing and simplify. So on number 1, if you expand this out, you can make this log base 5 of 1 minus log base 5 of 125. And then log base 5 of 1 is 0 because 5 to the 0 power is 1. And log base 5 of 125 is 3 because 5 to the third is 125. And there you get negative 3. Alternatively, if it was just simplify, then 5 has to go to the bottom of a fraction, which means the exponent has to be negative, and 5 to the third would be 125. So you could also get directly there using that rule. Number 2 is your ln of e squared plus ln of e to the 5th. So one way to do this is condense it. When you condense and it's addition, it becomes multiplication. And then when we multiply to exponential functions that have the same base, we add their exponents. So this would be ln of e to the 7th. And then ln of e cancels out. And what's left is your exponent, which would have been 7. Alternatively, if we simplified each of these separate, ln of e squared is just 2, plus ln of e to the 5th is just 5, and you get the same answer. So when we come to the test, any way you can simplify those is fine. Hopefully you remember one of those ways. All right, now these say specifically expand. So I'm going to take my multiplication and spread it out, making an addition. So this becomes ln of x plus ln of y plus ln z squared. And then you can't have any exponents when we expand. That gets bumped forward. So it's ln of x plus ln y plus 2 ln z. Number 4, we're expanding. Remember, anything in the numerator is going to be positive and anything in the denominator is going to be minus or negative. So I'd get log base 5 of x squared minus log base 5 of y squared minus log base 5 of z to the third. And then all my exponents bump forward. So 2 log 5x minus 2 log base 5y minus 3 log base 5z. Be careful not to lose the base on your logs when you expand. All right. Now we're going to get into the 3-4 notes. And 3-4 combines exponential and log functions into equations. So now we're going to be solving these exponential and log equations. There's a lot of different scenarios here, and usually one of the hardest parts is determining how to begin. So the first thing we're going to look at is exponential functions. And we'll know they're exponential because you have something being raised to a power. There is no log, no ln in your initial question. And with these, there are 2 ways to solve. The first is if you can change the base to be the same. So these we already did. These look like 2 to the x equals 8, and we would write that as 2 to the x equals 2 to the third, and then we would grab the exponents and solve. So if you can change the base to be the same, then we simply do that, use the change the bases to be the same, and then use the one-to-one property to solve it. Now the second, and what we haven't done yet, is if you can't change the base to be the same. And if that's the case, then you can actually log both sides of the equation, and you can take any log. You can log base 3 both sides of the equation. You can log base 10 both sides of the equation. Or you can ln both sides of the equation because that is a log. So we are going to actually take ln and make it a verb. And then we have to use the calculators. So this could look something like this. 2 to the x equals 7. There is no way to rewrite 7 as a base of 2. So instead, we ln both sides of this equation. I end up with ln of 2x, 2 to the x, equals ln of 7. And then I use my expansion rule to bump the exponent to the front. And then I would solve for x by dividing both sides by ln of 2. And then in the calculator, I would divide ln of 7, closing my parentheses, divided by ln of 2. And you get 2.807 if we rounded to 3 decimal places. Now, these will look like a lot of different things. Eventually, we'll have to isolate the exponents and all that stuff. But at the end, in order to get the exponent out of, or the variable out of the exponent, we will take the log of both sides of the equation, specifically the natural log, in this case, ln. All right, so here's what they look like. Notice, again, everything on this slide does not have a log or an ln in the beginning, which means these are our exponential functions. So the first thing we're going to try to do is see if we can give something with the same base. So when you look at A, 64 and 32 are both powers of 2. 32 is 2 to the 5th raised to the 2 plus x, and 64 is 2 to the 6th raised to the 3x. If we didn't know, then I would use my factor tree. You could do 8 and 8, and 8 is 2 and 4, which is 2 and 2, and the same here, 2 and 4, 2 and 2. That is 1, 2, 3, 4, 5, 6 2s. And I would have done the same thing with 32 and gotten 5. Now, every time we raise the power to a power, we're going to multiply here. So we'd get 2 to the 18x equals 2, distribute 5 times 2, which is 10, 5 times x, so plus 5x. And then as soon as the bases are the same like they are, we ignore the bases and we set the exponents equal to each other. So this becomes 18x equals 10 plus 5x, and then we solve our equation. Subtract the 5x, 13x equals 10, and divide both sides by 13. And x equals 10 over 13. So this type of question would be on the non-calculator portion because you can change the base to be the same and you don't have to ln both sides. Now looking at B, 5 is one base and the other one is 1 over 125. So we're going to rewrite 1 over 125. We did this in the warm-up, but I have to bring it to the top and I have to make it a power of 3. So this becomes 5 to the negative 3. And 5 to the 2x would equal 5 to the negative 3. Bases are the same, so ignore the bases and set the exponents equal to each other. 2x equals negative 3. Divide both sides by 2, and x equals negative 3 halves. And then we go to, actually we're going to do D first, and then we'll go back to C. We go to D. Now this is exponential, and there's no way to make 4 a base of E. So this is where we're going to ln. When we ln both sides of these equations, we end up with ln of e to the x equals ln of 4. And ln of e to the x actually cancels, giving you just x, because ln is log base e, so log base e of e to the x is just x. And that equals ln of 4. Without a calculator, I would leave it like that. But if this is on the calculator section, then I would use my calculator to find ln of 4, which is 1.386. We're going to round to 3 decimal places, unless it tells you otherwise. Okay, now go back to C. Very similar, except first we have to isolate the whatever is being raised to the exponent. So I'm going to add the 9, and I get e to the x equals 28. And then, just like we did already, we're going to ln both sides of the equation. Ln of e cancels, giving me x equals ln of 28. And ln of 28, 3.332. All right, Keep going with these. Example 2, solve the equation algebraically, and it tells you this time round to 3 decimal places. So now we got to do a little work on A to isolate the e to the x. So I'm going to subtract the 7, negative 2, e to the x equals negative 2. Divide both sides by negative 2, and I get e to the x equals 1. Now this is a scenario in which you could add on both sides, but you also can use your rules of exponents, and anything that's raised to a power to give you 1 means that that exponent has to be 0. If I ln both sides of this equation, ln of e cancels, I get x equals ln of 1, and log of 1, no matter what that base is 0. So it's another situation in which you could have that on the calculator portion of your test. If you hit ln1 in your calculator, you're going to get 0. But this could have also been done without a calculator. All right, now B looks tricky. And it's definitely weird and different from what we've already done. But once I teach this to you once, hopefully this makes sense. First of all, it's a trinomial. There's 3 terms. And if you look at the middle term and the first term is the middle term squared. So we can actually use substitution here. We can say e to the x equals a variable, let's say a. In Algebra 2, sometimes we used u or a. And we're going to replace e to the x with a, which means e to the x squared, or that first term is going to become a squared, minus e to the x is a, minus 12 equals 0. And now we're going to factor. So we're looking for factors of negative 12. That's sum to negative 1, which would be negative 4 and positive 3. Then we're going to split and solve, because if either of those parentheses are 0, the whole product is 0. And I get a equals 4 and a equals negative 3. But we're not done, because we made a replace e to the x. So now we plug that e to the x back in. So e to the x equals 4 and e to the x equals negative 3. Now we ln both sides. ln of e cancels, and I get x equals ln of 4, which we already did on the last slide. That's 1.386. And then ln of e over here cancels. I get x equals ln of negative 3. And you can type it in your calculator, but it's going to give you an error because you cannot find the log or natural log of a negative number. So the only answer that works in this case is 1.386. Okay, now the second type of problem that you're going to see in this section would be a log function. And you'll know it because the equation will literally have log or ln already in the equation. So there's 4 different ways to approach this, depending on the type of question it is. If there's only one log, for example, it says log base 3 of x equals 2. Then you're going to put that equation into exponential form and solve it. So the 3 would come over and pick up the 2, and I'd get x equals 9. These we have done already. The second type is if there's one ln. And in that case, we're going to convert it to log base e and put it in exponential form. So that could look like ln of x equals 2. I would rewrite that as log base e of x equals 2. Convert it to exponential, so e to the second would equal x. And this is a case in which if you didn't have a calculator, you'd leave it like that. And if you did, you would find e to the second, which is 7.389. Now the third kind is if there's one log on either side of the equal sign. And in my opinion, these are the easiest, because if that's the case, we simply ignore that log and we use the one-to-one property to solve. And that would look something like this. So it would say log x plus 3 equals log 10. And that base could be whatever it wants on the log as long as it's the same. So 1 on either side says 1-to-1 property, says ignore those logs. X plus 3 would equal 10 and x would equal 7. And the last type, which requires the most work, but if you know what you're doing is still not that bad, is if there are multiple logs. So if you have more than one log or more than one ln on either side of the equal sign, we're going to use the properties that we just did in 3.3, the properties of condensing, to condense it down to one log on the sides of the equal sign. And then if there's one log on either side, we would do what we did with the 1-to-1 up here. And if there's only one log on one side of the equation, or if there's only logs on one side of the equation, then we would use that first rule. Now, the most important thing here is this. Log expressions are defined only for logs of positive real numbers, meaning we cannot find the log of -10 or the log of 0. So we are going to have to check every single one of these answers to make sure that when they're plugged back in, what's next to the log or what you're trying to log is not 0 or negative. So it has to be greater than 0. So for example, if I had gotten log base 3 of x equals a number, whatever this is, and the answer I got for x was a -2, for example, and I plug this back into check, I'd be trying to find the log of -2, which cannot be done, so I would rule out that answer. If there's more than one answer, I would keep what works. If no answer works, then there would be no solution. But the most important thing to remember is that when it's a log equation, when it starts with log or ln in the equation, you have to check your solutions. All right. Now it says solve the log equation algebraically. Now, when you get to the test, it's just going to say solve. So I would have to know, oh, this has a log in it. This has an ln in it. Those are both logs, which means at the end, I'm going to make sure I check my answers. We're going to round these to 3 decimal places. All right, so go to A. There's one log on one side of the equal sign. So I'm going to convert this to exponential. Now, it just says log, but that means the base is 10. 10 is going to pick up the 2. 10 to the second would equal, drops off 5x. 10 to the second is 100. And then divide both sides by 5. And x is 20. Now I check if I plug that back in, does 5 times 20 bigger than 0? And it is. It'd be 100. So I know I can keep this answer. Go to B. There's only one log or ln, but I have to isolate it first before I can convert it to exponential. So I'm going to subtract the 5. I get 2 ln of x equals 9. Divide both sides by 2. ln of x equals, and I'm going to keep this as 9 over 2, but you could also rewrite that as 4.5 or 4.5. But because my calculator is going to get involved here, I'm going to let the calculator do that work. So this becomes log base e of x, because ln is log base e, of 9/2. The e picks up the 9/2. So e to the 9/2 equals x. And now I grab my calculator and I raise e to the 9 divided by 2, or 9/2. And I get x equals 90.017. And before I'm done, I check. If I plug 90 back into that x, am I trying to find log of a negative number or 0? And the answer is no. So I get to keep that answer. Continuing with our logs, example 4, same set of instructions. A has ln of x equals -3. So I'm going to change this to log base e of x equals -3. E picks up the -3, drops off, leaving the x. And e to the -3 is 0.017. 0.0497. So that 9, the 7's going to bump the 9, the 9's going to bump the 5, and this becomes 0.05. Checking to make sure when I plug it back in, it works, and I can find log of 0.05. It's bigger than 0, so I keep that answer. On a side note, these are easy to check. If I had my calculator especially, I would plug ln into the calculator, 0.05, and now I might not get exactly -3 because we rounded it. I'll actually get -2.995, but that rounds to -3. So these are easy to check when you have your calculator. All right, now B, the last one. This time there's more than one log on one side of the equal sign. So I'm going to condense this side. If I add, it turns into multiplication. So I get log base 3 of x times x minus 2 equals log base 3 of x plus 4. There's one log on either side of the equal sign with the same base, so I ignore those logs. I get x times x minus 2 equals x plus 4. I'm going to distribute here. I get x squared minus 2x equals x plus 4. Subtract the x, subtract the 4, because I know I've got an x squared and an x, so I'm going to have to get everything to one side to factor. And I end up with x squared minus 3x minus 4 equals 0. And I'm now looking for the factors of -4 that sum to -3, -4, +1. And I'm going to split and solve. I get x equals 4 and x equals -1. And I check. I'm going to check x in both, everywhere there's an x, I have to check to see if these work. So if I do 4 here, it's fine. 4 minus 2 is 2. That's still fine. And 4 plus 4 is 8. That still works. Now I have to check -1 in each of these places. -1 in this parentheses, -1 plus 4 is 3. That's positive. That's fine. -1 in this parentheses, -1 minus 2 is -3. That's not okay. So I can't keep it. Even if I had checked it here, -1 there would not work. So I rule out the -1 and I only keep where x equals 4. So now the tricky part will be if this is on your multiple choice part of a test, they will for sure include a solution that has the -1. Be really, really careful on these and make sure they work. Okay, last example. Example 5 says, again, same set of instructions, solve the equation algebraically, round to 3 decimal places. So this is that last case scenario where you've got 2 logs, but they're on the same side, and then there's nothing on the other side. So on that one side, we're going to condense these down. So it'd be log base 3. It's a minus, so this would be x divided by x plus 2 equals 2. And now there's only a log on one side, so we're going to convert to exponential. The 3 picks up the 2. 3 squared would equal x over x plus 2. So 9 equals x over x plus 2. And then we're going to get the variables out of the denominator by multiplying both sides by x plus 2. I'd get 9x plus 18, because that 9 goes to both, equals, it's canceled from here, x. Subtract the 9x, and I get 18 equals -8x. Divide both sides by -8, and I end up with x equals -18 over x, which becomes -9/4, which would be -2 1/4. You can answer any of those ways. But remember, we have to check these. So this is where it's important to make sure we take and we plug back in. If we plug -9/4 into either of those spots, so in the first one, it's just 9/4, which means we would rule it out. But also in the second one, this would be -2 1/4, and -2 1/4 plus 2 is still negative. And you can't find the log of a negative number. So this is a scenario in which there would be no solution. Or on web-assigned DNA, same thing, does not exist. What you could have seen a variation of this is these could have been LNs. So it could have been ln x minus ln x plus 2 equals 2. And we still We still would have condensed. And then we would have changed this to log base E. So the difference would have been there. The E would pick up the 2. And you would have your calculator on this kind of a question because you could keep going from there using that calculator. So remember, LNs are also logs. We approach them the same way. But when we go to solve, we change them to log base E's. Okay, that wraps up the note for today. Please, please, please submit your notes. And then use the remaining time to start the 3.4 homework. I will see you tomorrow. If you need any questions, obviously we'll go over this. We'll do the 3-4 warm-up, and then we'll start the review for your test on Thursday. Have a great day, guys.